All right, so good afternoon, everyone. I'm Devin. Welcome to Tea Time. We're in week 3 now. We're learning about different modeling techniques this week. So today I'll be talking about multivariate modeling, which is sort of a step up from the class of general linear models I think that we talked about yesterday. So let's get started. So sort of to contrast this with what we learned yesterday, we talked about, I think, just linear regression, and we mentioned multiple regression. So one thing that often gets confused or mixed up is the difference between multiple regression modeling and then multivariate modeling. So we started out yesterday with, I think, a simple linear regression, which was where we had some variable, a dependent variable, which we might call y, and we wanted to predict it with something x. And then we sort of advanced and built upon that to include multiple predictors. So like here I'm showing x1, x2, and then all the way to xp, so we could have multiple predictors for this model. However, when we go to multivariate modeling, we now want to have multiple responses or multiple y's that we're predicting. So here you can see that this y is a sort of a matrix instead of a vector now, and it has 2 dimensions. It has an I and a j. So we have multiple responses in this equation with the same predictors. So that's sort of just the intro to understanding what the difference is. So if we're concerned with doing both of them, we can have multivariate multiple regression. So we're fitting multiple responses with multiple predictors. And we just want to do this. So the goal here would be to fit a model for multiple correlated responses and multiple predictors. The reason that we'd like to have correlated responses is that if they're uncorrelated, it wouldn't really make sense to try to fit them together, because you might fit one of them very well and the other one would not be fit so well by the model. This isn't a blanket statement. It can still work out to work well, but that's sort of just a general thought process. So first you'd like to check the correlation of the responses. Then you would go through your standard steps for fitting like a general linear model. You do variable selection, fit it, and then you might want to do something like ANOVA testing or analysis of variance. Just to look at some of the math, I won't sort of go deep into fitting in least squares and things like we did yesterday, but this is sort of visualization of, okay, so here we have n number of observations. This would be like if we just had some y values that we're trying to fit, but now we have this for multiple responses. So this could be 3 or all the way out to as many as you wanted. This X matrix is the matrix of our predictors, and P is the number of our predictor variables. The B here is actually the beta. Got mixed up with the math, so I used B instead of beta here. But this is like the coefficients of the model, so you have the same number of coefficients for each response. And then E or epsilon would be our error terms. We have the error for each predictor and each response as well. And then it's similar to the linear regression, we want to minimize the residual sum of squares. This is sort of what we saw yesterday. And now this summation here on one variable turns into a double summation just because we added in now that we have m number of different responses. So everything scales the same way. You just do it for multiple responses. It's almost just like fitting, simultaneously fitting more than one linear regression model at the same time. And then looking at the fundamental assumptions, they're very similar, once again, to multiple regression. So we assume that the relationship between our x's and y's is linear. We assume that the x's and y's are observed random variables that are known constants. We assume that the error matrix is, we don't know the errors beforehand. It's a random matrix. We don't know the betas, they're unknown. And then we assume that the homogeneity, homogeneity of variance for each response. So that's like looking at, we saw the residuals yesterday, and that we don't want any trend in our residuals. And we can also look at that for our multiple responses as well. And potential issues, they are the same, but we could obtain relatively poor fit for some responses if we have that our responses aren't very correlated, or we have some variables that are significant for one response, but not significant for the other. So that's something to consider when fitting multivariate. And so now we can look at a demo how to do this in R. So I coincidentally am also using the mtcars package, and I'm gonna read it in with one line, and I sort of added in, I wanted to reshape the order of the columns. So that's why I have some extra numbers there. And just in case we're not familiar with what the mtcars data set is, can you see this? This is sort of hard to see. So it just has, it's a data frame with 32 observations on 11 variables, and it's basically data on cars, things like the fuel economy, how much they weigh, the quarter mile time, etc. And so this is the data set that I'll be using to model. One good way to visualize the data is to make a pairwise correlation plot. And I will have to do zoom on this for sure. So yeah, this came out small. Hard to see. But so along the diagonals, we have all of our variables going down. And I purposely arranged this such that the two responses that I'm interested in are the first two. So I'm going to try to be interested in looking at if I can predict the fuel economy in miles per gallon, and also the QSEC, which is the quarter mile time. So how fast can the car drive a quarter of a mile using the number of cylinders, the displacement of the engine, horsepower, the drat, I forgot what this one means, the weight, whether the engine is vertical or V-shaped or straight, automatic or manual transmission, the gear ratio, and the carburetor. And so in the upper right portion of this, we have sort of the correlation coefficient of the variables with one another, and in the bottom right, we have a scatter plot, or bottom left, we have a scatter plot of the data versus one another. So this is a really small number here, but you can see that there's a 0.42 correlation between these two variables. So that may not be very high, but I'm going to try to make a multivariate model with these anyway and see how it turns out. So there's this package QT LMT that I'm going to be using in my modeling. And if we do a search for the package info, it doesn't actually come up. So this package is not very well supported. If I do a Google search, find it. So this is actually made for mapping multiple complex traits, but it actually has some tools inside of it that I found useful for doing variable selection for multivariate models. So what I'm going to do with this is do a forward stepwise selection. What you do in this method is you start with a null model. So you're saying that your model, your responses are being modeled just by one. So they're just a straight line. And then you give it a full model. So that's here just showing like this would be trying to build a linear model LM with two responses, with one as my predictor. And then the full model would be is using the period. This includes all of the rest of the variables in the data frame. And then the mstep function will take one variable, add it in, and then see if this variable is significant for the model. Then try to add another variable in, and it will go through that process iteratively and find which variables are significant for the model and which ones are not. So if I run these lines, I first define the null and full model. And then if I run this function, direction is forward. That's sort of, you can actually run this in reverse. You can start with a full model and then subtract variables. That would be backwards selection. So if we resize this panel, it actually prints out and we can watch how the model works. So we start with our null model, just being one, and it considers adding each of the variables to the model and seeing what compares the AIC value. And so the AIC value is the Akaike information criterion, and it sort of allows us a lower value of AIC is what we would like to minimize the AIC. So the first variable that it picked out to add would be weight. You can see this. In the AIC, it gives you a starting AIC value. And then it will try to add in the next value that reduces the AIC the most. So the next one was horsepower. The third was the VS And then the fourth was automatic or automatic or manual transmission for the car. And then it gives us, that's our final model. So taking that, I can then build my multivariate multiple regression model with the LM command, just like building a multiple regression model. You just use cbind for the given number of responses that you want. And then you get the model object, and then you can run summary on the model to see what's inside. So it gives you the summary of the model results for both responses separately. So for the first response, MPG, we can see the significance of each of the variables and their standard errors, the estimates, and the p-values. So here we got an adjusted R-squared value of 0.8277. So that's explaining about 83% of the variation in the data for MPG. And if we look at the second response, the quarter mile time, you can see that the variables look to be more significant for this response than for the first one. So that's what I was talking about earlier. You'll have to consider, if you're fitting both of them, you want them to both have the same predictors, but some of them may be more significant for one response than the other. And here we got a lower value of adjusted R-squared, so it doesn't actually fit both responses equally, but it does do the job for us. And then we can treat this model just like any other linear regression model object. We can, if we want, we can take out the coefficients and residuals and effects, same thing that we saw yesterday. If we wanted the coefficients, we can run coef on the model, and we can get out all the different coefficients there. So we can interpret these the same way as looking at, as we did yesterday. We could say if we had for a unit change in weight, our fuel economy would go down by 2.59 miles per gallon. But if we, our quarter mile time would increase by 0.75 seconds for a change in weight. And then if we wanted to, for example, run analysis of variance, there's actually a multivariate version of the ANOVA function in the stats package. And this is for multivariate analysis of variance. And it effectively does the same thing as ANOVA, but for multivariate models. ANOVA testing, we can use it to look at, basically it considers the model without each of the variables, and it's another confirmation that each of the variables is significant for the model. So using this, we can get out here the p-values for each of the predictors of the model, and we see that they are all significant for this multivariate model. So even though we find that for some of each response has a different significance level for each predictor, for the model overall, all of the predictors are significant. And then if we want to do prediction, we could, I'm just going to steal a few select lines from the MT-Cars data set, and this is going to be my data that I want to do prediction on. So if I have a Honda Civic and a Toyota Corolla, and I wanted to see how my model predicts on these, I could just run the predict function on my model and give it that data set, the pred data. And then looking at, predict, so I can see the fuel economy for the Honda Civic is slightly better than the Toyota Corolla predicted by my model. And the quarter mile time is slower. So functions quite nicely. And then if we want to look at the residuals to do diagnostic testing on the model, we can get the residuals by using the fitted function, or the fitted values by using the fitted function. We get the residuals by using the resid function. And I'm just going to store those separately and then make a plot of these. So for each response, it's actually indexed. If I go into one of these, we get out the residuals for each response in columns. And then if we want to plot those to look at how they spread, we can make a plot like this. So for response 1, we see that our residuals are fairly random. There's not much trend between them. It's a random spread, so that's good. We do the same for our second response. You may be able to say that this sort of fans out a little bit. So we could check the quality of the data before we fit our model. We wanted to look at the normality beforehand. And then another thing that's usually done on regression models is looking at quantile. So this works as well for multivariate models. We would like for our QQ norm line to fit the points in it. We like them to fall in a straight line, but there's some deviation at the tails. This could speak to some of the high leverage points in the data. So that's the wrap up on multivariate multiple regression. Takeaway or main point is that it's mostly very similar to a multiple regression or just like regular linear regression, except for you can use the cbind function to fit multiple responses simultaneously. So a second topic that I'll be talking about is principal component analysis, or PCA. This is a technique that's commonly used for dimensional reduction or for feature extraction on data sets, and it's also known as SVD, or singular value decomposition, or an eigenvalue decomposition. You might have learned this if you've ever taken the multivariate calculus course, and it's pretty straightforward formula. You have that there are eigenvalues that are equal to your data metrics times some eigenvectors. And these might sound complicated, but we'll walk through it and see what exactly those mean. So what it does is that it reduces the data set into a group of uncorrelated variables. All of these are orthogonal. And these are what are called principal components. And the number of principal components that you get out of this is less than or equal to the original number of variables. So if I put in 18 pieces of information, it will be reconfigured into 18 principal components that capture a certain number of variation in the data. And they are ordered in the amount of variability that they account for. So we could reorder our data, and most 90+% of the information can be captured in the first principal component, when that's how you accomplish the dimensional reduction. And the outputs are things that are called loadings and scores. Loadings are the eigenvectors, and the scores or weights are the eigenvalues. So this is sort of a little picture that describes how it works. You start with some data set or vector, and then we basically are searching for this matrix of A's, which are our scores, that is equal to lambda times the original data. And that's sort of the transformation there. And where this is used, a simple picture, if we have a data set, just X's and Y plots in the graph, then if we did PCA on this, so it's best described by this first PCA dimension, that would be, for example, like fitting it with a straight line. And then there would still be some error from that straight line. But we get most of the change in the data occurring in this direction, so that if we wanted to reduce the dimensionality, we could just reduce this down to the variation on this axis. And then if we wanted to also look at the rest of it, we would take the second direction. And this is also used in facial recognition or pattern recognition. So let's say we had 18 pictures and we put them into PCA algorithm, it would split it out into these 18 different components, which we could put together to get the original face back. But if we just wanted to look at what are the main features that make up a face, it might be something that looks sort of blurred like this, something a little more creepy like this. But once you put all these features together, you could get the original face.
When you say together, is that a summation?
Yeah, so it would be like taking these scores or weights and then multiplying them with their associated loading or eigenvector. Yeah, so if you take them and sum them back together, you would get the original piece of data. So in R, how we do this, I'll be using the iris data set for this example. So if we take a look at what the iris data set contains, it's a data set on flowers. So it has the sepal length, the width, and then the length and width of the petals, and then they have different species of flowers. So let's say I wanted to group these flowers together by some of their characteristics, but I have 4 features that I'm trying to weight to group them together. It would be more convenient if I just had one feature, sort of reduce that dimensionality of 4 down to 1, so we have one way to sort of group those by. We could use PCA to do that. So the function that I'm going to be using is the PRComp function. It's also from the stats package. It takes in a formula, and then it needs a data frame, and those are pretty much the 2 important things that we need to give it. So to do this with our iris data set, so our data set's going to be iris, and then we're going to give it that we want our response or to be a function of the 4 different characteristics of our flowers that we have. I'm going to store this as PCA iris, and then I'm going to look at the output. So we put in 4 characteristics for these flowers, and we get out 4 principal components. And then we can look at the relative importance of those components. So we see that the first PC contains 92.4% of the variance in the data there. And our second one contains about, 5.3%, and it shows you the cumulative at the bottom. So we can see that we could just take this first principal component, and if we wanted to sort of cluster based on the weights of this first PC, we would get most of the information contained in that data set without needing to use 4 variables. We could just reduce that down to 1. You can actually run plot on these, I believe, as well. And this gives you a visualization of what the relative variance looks like for each component. So this is sort of showing you that most of the variance is captured in the first component, and as you go across, it goes down. You could also make a biplot. And this biplot is sort of showing what the results look like. So this is sort of a messy plot. PC1 is our x-axis here. PC2 is our y-axis. And then each of the numbers inside the plot is one of our observations or one of those flowers in the data set. So you can see that they sort of naturally group themselves based upon whatever the relationship between how well they're described by PC1 and PC2. And then the arrows try to point out how the 4 original features are, which direction describes those original features. So if I had a nicer plot and I colored them, which I do in the slides, you can actually see that that plot groups the flowers quite nicely by their different species. So on the left side, we had the Setosa and the versicolor and then the virginica. So the PCA sort of allows you to do clustering if you take the weights from the eigenvalues and group them that way. And then another example I'm going to be showing is from chemistry. So then I'm going to be using some FTIR spectra in this. Infrared spectroscopy is used to identify molecules and different functionalities. So I'm going to load, I already have a data set made up for this. And I'm using the HyperSpec package here. So what's inside of this is we have 42 different spectra. We have some metadata about these different spectra. So they're measured on some different plastic films that I have, and I'm studying them over time. If you look at what the data looks like, just to get an idea. Yep, so what's going on in FTIR spectra is that we have this x-axis of wave number, which is the energy that we're using here to measure these samples. So we put in some energy into our plastic film material, and then it's absorbed, and we look at how that light is absorbed. and how the light is absorbed at these different energies tells us about the structure of the material. So we're looking at some characteristic of these materials that changes with this value time. So time here is in hours. So over time, there's something going on with the structure of these materials that we can track through the changes in these peaks and valleys. And so if we wanted to figure out the main changes in this, we could use PCA as a tool to sort of decompose that. So I have a few lines of code that are just corrections to my data. And then PRComp has a nice functionality if you're working with spectral data using the Hyperspec package, that you can run it directly on this Hyperspec object. We can look at the summary again. So this time, it's quite a lot bigger. So I put in 42 different of these FTIR spectra, so I got out 42 principal components. So that's quite a number of principal components to consider. I may only need the first 2 or 3. So one thing you can do is that you can change the rank input here. So the rank of the principal component analysis gives you a different number of principal components. So if I set it at 3, I'm only going to use the first 3 principal components. So it still tells me that I would have gotten 42, but now I'm only taking the first 3. So the first one captures about 90% of the variation in the data. The second one adds about 6 more percent, brings it up to 97, and then the third, another percent. So that's much more usable and reasonable for us. So that means that the last ones probably just have noise inside of them. And then I can separate, I can use this decomposition function. What this does for me, it just basically extracts out the scores and the loadings. I can store those in 2 different R objects. This is another way to visualize the variance explained. So since I have 42, you can see that this is just another way to look at it. The vast majority of the variation is explained by the first principal component here, which we know is 90%. And then if we take a look at the loadings and the scores here, I'll plot the loading of the first principal component. So it looks something like a weird mangled version of our original data, but this is actually pretty informative to us. So what this means that the main changes that are happening in that between those different spectra is that this peak is sharply going up, this one is sharply going down. We have something rising up here, we have some dropping here. So this is actually sort of like the main differences between those spectra. This would be looking at, this is the main change happening over time in this feature. So then if I plot the scores of this principal component, since our samples were measured over time, this index from 0 to the 42nd sample is actually a measure of how this feature is expressed over time. So if we know that this change is being caused by some degradation reaction or some mechanism in our material, we can actually look at sort of, this is the sort of a pseudo rate of reaction for us, since this is versus time. And if I look at the second loading, we can consider this like sort of a secondary mechanism that's going on in this FTIR spectra. This is sort of a second difference, and it would have maybe not as strongly of a linear shape, but it might be more scattered. So this is sort of indicative that most of that change between those spectra is captured in the first principal component. It follows a pretty linear trend over time, which actually goes along with what we know from chemistry. And then the second component and forward is sort of just like the noise in this data. That's why this is sort of just going up and down over time. That's actually just like variation or noise. And then we could also do this for the third, but that would look about the same as the second. So overall, multivariate modeling is quite useful when you're handling data with multiple responses, or you want to do some sort of dimensionality reduction on your data. Yeah, so we've learned about multivariate modeling in PCA. Does anybody have any questions on how they could use these or what any
your demo.
This one?
No, the
The demo.
composition on the demo.
Mm-hmm.
You had that
Oh, yeah. Okay.
name.
This one.
Yeah.
We can look at it. So it's a function in the hyperspec package, and it's specifically built to convert this principal component decomposition into something like a hyperspec object. So the output of the PCA object stores the information like the loadings and the scores and the variances and things. But this function sort of reconverts that. Since I was handling spectral data, it just sort of converts it back into something that I could plot as a spectrum instead of having the data sort of convoluted in that PCA object. It's just a tool that makes it convenient to flip back and forth between two different types of objects. Since I was handling spectral data, I was using this function to convert it from the PCA output back into a spectral data set. Does that make sense? Yeah. Okay. Well, if there's no more questions, then I thank everyone for coming. And tomorrow we'll be looking at, I think, generalized additive models.